lesson you've got for us today, as well as tomorrow's final lesson.
Excellent. Thank you, TJ. Hi, everybody. My name is Christine Maceo, and I'm coming to you again from Annapolis, Maryland, from the United States Naval Academy STEM Center for Education and Outreach. Again, I want to thank the Air Force, Edwards Air Force Base, for inviting me to participate in this program with you for this week. And I would also like to thank the sponsors of this program, which include DoD STEM and the Office of Naval Research. And so we today are going to be studying cryptography, and you should have been able to download and print, let me just spotlight this, a set of worksheets that look something like this. So they look confusing right now, but they won't be confusing shortly. So if you could get those out, then we can work on this together. So if you feel inclined, I would encourage you to put your decryptions into the chat so that we can make this an interactive experience, and so that we can share the work. So anyway, so what we're going to talk about tonight, like I said, is I called it globally cryptography, but we're actually going to learn about something called, I'm going to re-spotlight this. We're going to talk about cryptography, and cryptography is the art of writing secret messages. And we're also going to be talking about cryptanalysis, which is the art of reading secret messages. The general topic area is applied math, and you'll see that we will be adding math into this. And actually, as far as the research in this, it is in the mathematical field. So cryptography might seem like a new topic, but it's actually been used for thousands and thousands of years. Probably in modern history, it was used for, and really in ancient history as well, it was used mostly for government and military operations for security purposes. But now that we are in this digital age, we're finding these skills are useful and that you use them every day. So every time you type a password into a phone, every time you log into a website to buy something from an online retailer, every time you do two-factor identification, you are participating in cryptography, and it is central to our lives today. So we're going to talk about a specific type of cryptography today called a cipher. And a cipher is a way of changing each individual letter. So you're still going to spell words in the type of cryptography that we're looking at today. You're just not going to spell them in the traditional sense like we learned how to read. And like I said at the beginning, Julius Caesar is known to have used cryptography. In fact, we have a very famous cipher that's named after him called the Caesar cipher, also called the shift cipher, but he was using that in 50 BC. So more than 2,000 years ago, he was encrypting his military strategies with a shift cipher. So I am going to show you the cryptographic tool that we're going to use today. So right now it's blank, but we're going to fill it in just so I can show you what we're going to be doing. We're going to be using something called the Cipher Strip. And it's on the top of a lot of the pages that I sent you today, because this is going to be our tool. This is where we're going to make our decryption tool on a cipher shift like this. Like I said, you'll still be spelling with the ciphers that we use today. So I wrote our alphabet at the top. So that's traditionally what you would expect to be spelling with and reading with. And underneath each letter, I left a blank. And we are going to be filling in those blanks with whatever we're substituting the letter with. So that is what we will use for our cryptographic tool today. All right, so I did mention that Julius Caesar used a cipher to encrypt his military strategies. And he used a shift. He always used a shift of 3 letters. So if you look at the screen again, what I did was I have that same strip at the top with our traditional alphabet on top. And this now I'm going to label it. I'm going to call it plain text. And plain text is just what it sounds like. It means what you would expect to read in the language that you speak and read. Underneath, I have what's called ciphertext. And that ciphertext is what I'm actually going to use to encrypt my messages. Now, when I say that Caesar always used a 3-letter shift, if you look at our alphabet on the top line here, and then you look on the bottom line and find the A again, you'll see that it's 3 letters away from the A in the regular alphabet. And so that's what I mean by Caesar always shifted his messages by 3 letters. All right, so what I wrote underneath was Veni Vidi Vici, so one of Caesar's famous quotes. And what I wanted to show you is how you would encrypt Caesar's message using this cipher strip up here so that we can then get to the exercises that we're about to use so that you know how to do it. All right, so this Veni Vidi Vici is in plain text. So he spoke Latin, so I wrote it in Latin, but it's still considered our plain text. What we want to do is encrypt it. So we want to get the ciphertext equivalent from our Caesar, our shift tool, our cipher strip up top. So the way we do that, and I'll do this in blue, is this V is in plain text. So I will go up to the top row of the table and find the V, and I replace it with the letter that's directly under it. So that V will be encrypted with an S. So one of the reasons I picked Veni Vidi Vici was because Caesar said it. The other reason is it has a lot of repeated letters. So because this is a stagnant strip, it's not going to change once I set it. I can actually put an S under the 2 other V's that are part of this message. The next letter that I need to encrypt is an E. I'm going to go up to my plain text until I find an E, and then I'm going to encrypt it with the letter below it, which is a B. And I would continue to do that for every letter in the message. And really there aren't a lot left, so let's continue to do that. Next letter is an N. So I go up to the top row, find the N. That's encrypted with a K. And the I is the one I'm really excited about because I actually get rid of a lot of letters here. I'll go up to the top row to find that I. Right under that is the F. So I'm going to put the F under every I. And when I do that, I have encrypted most of my message. I only have 2 letters left, and they actually are right next to each other on this cipher strip. So the first one is a D. So I go up to the top row, I find the D. It's encrypted with an A. And the C was right next to it, and it's encrypted with the Z. So that's how I would encrypt with a cipher strip with a shift of 3, which is the one that Caesar used for all of his military strategies. Just to show you a little bit about how we would decrypt, if I had gotten this message, SBKF, I would decrypt by using that same strip, but in the opposite way. This time, what I would know is the ciphertext. So I wouldn't go to the top row of the table. I would go to the bottom row of the table. I'd go over to the S, and I would decrypt by finding the letter above it. And it would bring me back to that page. Are there any questions about that type of encryption method? You can feel free to put that in the chat. All right, so I'm going to remove the spotlight, bring it back to me for a second. All right, so Caesar always, I told you, and we just worked through an example of Caesar always using the same shift, always using a shift of 3. So that actually, does that sound like a safe practice to you? Always use the same shift. It's kind of like always using the same password. I'm sure you've been told many times not to use the same password for different accounts, to always make sure it's different. If you use the same password, it increases the chance of somebody being able to get at not only your information, but all of your information. So nobody actually hacked Caesar's ciphers in his time. And there's a good reason for that. It was safe for him to always use that same encryption tool because he lived, first of all, he lived in a time when people were not very well connected with each other. So it just wasn't as populated as it is now. And then during his time, not a lot of people went to school. So not a lot of people could read anyway, much less read with the alphabet shifted by 3 letters. So we live in a very different time. So we have to be much more secure than Caesar would have. So anybody want to put in the chat one way about how to make the Caesar cipher more secure rather than using a shift of 3 each time? Well, one way to a random shift. So yes, a random shift. So we actually have in our alphabet, we have 26 letters. So he didn't quite have 26 letters, but we have 25 different shifts we can choose from. We don't always have to use the number 3. So we can use different shifts for different messages that we can encode. And it increases our security because there are just more options to try. So that is actually what we are going to do right now. So I'm going to spotlight back to the worksheet and show you the one that I want you to take out right now. So it looks like this. You have a worksheet numbered 1 through 5 with a blank strip on top. So we're going to actually set up the strip ourselves. And what we're going to, what we're going to do is we're going to decrypt these 5 words. So I actually want you to take out 2 sheets. I want you to take out that sheet. And then I want you to take out a puzzle sheet that looks like this, that also has numbers on it. So numbers 1 through 14 over here, because this is going to be where we put what we decrypt. Let me just get that centered. All right. All right, so we're going to start with this sheet first. Now I told you that Caesar always used a shift of 3 and that we were going to use something different here. So before we can even start looking at this sheet of paper, I have to give you a piece of information. And what I have to give you is something called a key. And I have to give you the key so that you can set up the alphabet on this cipher strip so that you can start to decrypt these messages. And for now, I'm going to tell you, I'm not going to give you a shift of 3 or a shift of 8. I'm going to give you a letter as a key. And I'm about to tell you what that means. So my key is little r. And what that means is that is where I'm going to start writing my ciphertext alphabet. So I'm going to find the letter R, the little r, and that's where I'm going to put my A. And I like to write in capital letters for the ciphertext part of this because it helps me remember which way I'm going, whether I'm encrypting or decrypting. And once I know where to put that letter A, the Caesar shift keeps the alphabet in order. So then I simply continue to write the letters of the alphabet in order in these little boxes. And when I do that, you can see that I have I hit Z. I ran out of room. And so the way the Caesar cipher works is then you wrap around and you go back to A. So where we left off, we will go back and finish writing the alphabet in order. It's really easy to see if you make a mistake with these because you will either run out of letters or run out of boxes. So I always think it feels good when I get back to Z and I have no empty boxes left. So this is my cryptanalysis tool now. This is what I will use to decrypt these 5 words over here. So what I thought is that I would walk you through the first one and then ask you to put in the chat what you get for the next ones. So we'll do number 1 together, which is the one up top here. And we're decrypting, which means we have ciphertext and we're looking for plain text. So for this particular one, I'm going to find the H on the bottom row and I decrypt it by writing the letter above it. And that is a little y. Then I go over to the next letter, which is an N. And I write the letter that's directly above it. That's an E. And again, I always get excited when I see these double letters because it means I only have to do the work 1 time and I get 2 answers. And what I need to find here is a U, which corresponds to an L twice. Then I go back to the bottom row, find the X, goes to an O. And finally, I go all the way down and I look for that F, and that's W. And so that word, HNUUXF, decrypts to yellow. So, so I got some chats already, so I'm going to assume that you will decrypt these and put these in the chat. So I'll give you a minute to do number 2. So somebody already wrote, yes, number 2 is dogs. And if you have questions, so I'm going to write down what people put into the chat, but if you have questions, make sure you ask. How about number 3? T, yep. Number 4. Number 4 is a long one, isn't it? Yes. Rainbow. And number 5, it was deceivingly simple because it had 2 double letters. It is coffee. Yes. All right, you guys did great. All right, so we have filled in and you successfully used the Caesar cipher to decrypt these 5 words. There are 3 odd words, or I'm sorry, 5 odd words for me to put on a single page together, but that's why I asked you to get out that additional sheet of paper. So when I do cryptography with students, I like it to lead somewhere because then it feels like they are working towards something. So, and cryptography uses a lot of logic. In addition to using these cryptographic tools and this little cipher strip, I'm sure when I typed when I wrote in YELLO, that you had already filled in the blank with W because you started to recognize that word. So what I finished the cryptography with, and I just picked this one for today, is some kind of logical puzzle. So what I did was I gave some of the clues. There's 14 clues to this puzzle. I gave most of the sentence and I left one word out. And those blanks correspond to the words that are on this sheet. And the numbers here on the sheet correspond to the numbers here on the puzzle. So that means that I will fill in the blank for number 1 with the word yellow. And that makes that clue, the Brit lives in the yellow house. The blank for number 2, I'll fill in dogs. The Swede keeps dogs as pets. The blank for number 3, I'll fill in tea. The Dane drinks tea. The blank for number 4 was rainbow. The house colors are arranged in the order of the rainbow. And then the 5th one is coffee. And that makes that clue, the owner of the greenhouse drinks coffee. And we'll be doing 2 more cryptographic techniques today. And we'll fill in the rest of this puzzle, the clues anyway, and hopefully we'll get through the puzzle this afternoon. All right, so let me cork this Sharpie so I don't write on myself, and I'll come back to you here. All right, so we just used the Caesar cipher and we changed the key. So we did a different shift than Caesar did, and we realize now that we have actually 24 other options than the R we just used, one of them being ciphers. There are 26 letters in the alphabet. If we use that 26th shift, we get back to the alphabet. So that would not be useful for encryption. So that might seem more secure. So at least somebody would have to work 25 times as hard to decrypt a message that they found that was encrypted with the Caesar cipher, because they don't know which of those 25 letters was used for it. But despite the fact that we increased the complexity by opening up more shifts, the Caesar cipher is still a very easy cipher to crack. It has one major weakness. Does anyone want to put that in the chat? What's that one main weakness of the Caesar cipher? Yes, you only need one letter to break it. That's exactly right. As soon as I told you that the key was R, you were able to set up that whole strip and you didn't have to know any other information, and there was no way to go wrong unless you skipped a letter or wrote a letter twice. So we really want to be able to scramble our ciphers a little bit to make them more secure. So we're going to look at a different type of cipher that just gives some variability to the alphabet. So it makes it a little bit more difficult to crack. And what we're going to use for this one is the keyword cipher. And so I want you to take out the sheet that's labeled 6 through 10. So it looks a lot the same as the sheet I just gave you. And it will look a lot the same until I tell you what we're going to do for the keyword cipher. So I'll give you a second just to get that out. And again, this is missing a key. And so I'm going to teach you how to use the keyword cipher as I give you the key. And then we'll decrypt the first one together, and then I'll send you off on your own again. So again, alphabet up at the top, blanks down on the bottom. What's missing is a key. Key's gonna look a little bit different this time because it's a keyword cipher. So I'm going to give you a word, and this cipher can increase in complexity with an increase in complexity of the word. So I'm giving you a pretty simple word, dog. And I'm going to give you a letter. And that letter is J. And what this means, what this key means here, is I find the little letter J on my alphabet, my top row alphabet. And right under it, I start writing the word dog. So the D will go under the J, the O will go under the K, and the G will go under the L. After that, so after that G, I start writing the letters in order again. So I'll start with A, not H, but I go back to the beginning of the alphabet, or the first unused letter of the alphabet. And then I start writing the order. The difference here is that when I hit a letter that's already been assigned, because it's in the keyword, I skip it. So after the C, my hand wants to write a D, but D's already assigned, so I have to skip it and go to an E. Then I go to F. I want to write a G, but I already have a G, so I go and I skip it and I go to the H. And I continue in that way in order. And I keep going. Every time I reach a letter that I've already assigned, which I assigned the O already, so I'm going to skip it again. And again, when you hit that Z, you wrap back around and you continue in the alphabet in order. This one I suggest you do in pencil the first couple of times because your hand really wants to write the alphabet in order. After you set up the cipher strip and you do it with that keyword, the decryption or the deciphering is exactly the same process. We're going to do exactly what we did with the Caesar cipher, but if I now know that E is under P, I don't necessarily know that where the rest of those letters are. It would be hard for me to decrypt it. All right, so again, we will do the first word together, and then I will send you off on your own to do the remaining words. So decryption means I'm going to look at the bottom row for my first letter. So that happens to be an E. It's under the little P. So I decrypt the E with a P. Z is my next letter. Go over to the bottom row, find the Z, goes to an I. Q is my next letter. I have to go all the way to the end. And I decrypt that with the Z twice. So we're always happy when we see that. And R, this final letter, you've probably already filled in the breaks with your brains, but it goes to A. So that word decrypts to pizza. All right, so 7, 8, 9, and 10, I will leave to you to do. And you can put the answers in the chat. Anybody get number 7? Red, yes. 7 is red. Milk for number 8. Anybody get number 9? First, yep. And number 10. All right, so again, same decryption technique. These are the words now that you'll put in for the clues 6 through 10 on the bottom, on the last sheet that I sent you. So the owner who eats pizza has birds. The owner of the red house eats donuts. The owner of the center house drinks milk. The Norwegian lives in the first house. And the owner who eats burgers lives immediately to the right of the one with cats. So now we have the first 10 clues of on the puzzle. And we are ready to move on. So that should have felt much more secure to you than the Caesar cipher did, because you would have, if you had decrypted it and found out how one letter was associated, you wouldn't necessarily know how the other letters were set up unless you actually figured out what that key word was and that key letter was. So that is more secure, but it's still not super secure. And so really anytime that we're changing, let me get back, let me put me up here. Anytime that we are changing letters into other letters with some kind of letter technique, we're limited in what we can do because we're limited in how we write. We can use words only when we are changing letters into other letters. If we really want to add complexity to cryptography, what we have to do is add math, because if we do add math to our cryptography algorithms, then what we can do is anything we can do in math, then we can do to letters. So we can add them, we can subtract them, we can multiply them, we can exponentiate them, we can graph them, we can do anything we can do with regular numbers. So that would be the goal, to introduce some kind of mathematical functions into these letters, into these words, and that's actually where cryptography is today. All right, so before we go over how to do that, I'm going to repin this, or respotlight this, and I am going to ask you, you can put it in the chat, what is 9 plus 5? Right, 14. All right, so 9 plus 5 is 14. I'm going to ask you another question. If I start studying at 9 o'clock p.m. and I study for 5 hours, what time do I stop studying? Right, 2 a.m. So if I were to write that last statement in words, what I would get is I started studying at 9, I studied for 5 hours, I stopped studying at 2. So I actually gave you the exact same problem. You answered 2 different ways, and 2 different ways that were 100% correct, but they're different answers. So what's the difference here? The difference here, when I asked you the first time, I didn't limit the numbers you could choose from. You could choose from any number you wanted, and you chose the right one. You chose 14. The second time, I limited you to the clock. You could only use the numbers of the clock to answer that question. So you might have even pictured a clock. Is that all right? I'm going to start at 9. 1, 2, 3, 4, 5. My answer is 2. What you probably did without even thinking about it is that you knew there were only 12 numbers on the clock. You really wanted to say the answer 14, but you knew it wasn't one of your choices. So you divided 12 into 14 and got a remainder of 2, and that was your answer. So those are 3 different ways of looking at the same way I asked you that question. But however you look at it, you were limited to the 12 numbers on this clock once I asked you that question as it related to time. If we're limited to 12 numbers, we call that a modulus. Oops, can't see that. Modulus 12, meaning I only have 12 numbers to choose from. So actually, the more correct way to write the answer to the second problem here is 9 plus 5 equals 2 mod 12. And this other way of looking at it with long division, we divide the modulus into our sum, and the remainder is our answer. All right. So we have a clock with 12 hours because our day has 24 hours in it, and it made sense. If you were here at the Naval Academy, your clock would have 24 hours in it, but it made sense to make our clock have those 12 hours. If we're going to start using math with the letters of the alphabet, we want to do something similar, but we don't want to use just 12 numbers because we have more numbers than that in our alphabet. We have 26. So we want to assign the letters in our alphabet numbers, but we want them to be 26 numbers. And so when we start talking about assigning numbers to letters, we are in modulus 26. Any questions before I go any further? All right, so one thing to notice is that when I assign the letters A through Z to numbers in mod 26, I actually start at 0 and go to 25. I don't go from 1 to 26 like on the clock. And the main reason for that is I'm interested in remainders when I'm in modular arithmetic or when I'm looking at modulus numbers. And so you want a remainder of 0 rather than a remainder of 26. 26 is not a remainder if you're dividing by 26. So we go from 0 to 25. This is not an encryption technique. This is going to be a technique to just change the letters into number. A goes to 0, B goes to 1. That's just a substitution. That's why I called this alphanumeric substitution. What I want to do is encrypt on top of the alphanumeric substitution. So when you were learning math, what was the very first operation you learned how to do? Somebody can put that in the chat. Addition, yes. And so the simplest cipher using math is called an additive cipher. And we're going to go through how to encrypt with the additive cipher. All right, so hold on, push this up. We're going to encrypt the word STEM using an additive cipher. So first of all, I need to give you a key, and the key that I'm going to give you is +8. So that means I'm going to encrypt every letter here with a +8. That's my key. Now, can I add an 8 to an S? No, I can't add an 8 to an S. So my first step for the additive cipher is to change the word that I'm looking to encrypt using alphanumeric substitution. It's up here. So we're going to use alphanumeric first. And that means I go to my chart, I find an S, it's an 18. I go to my chart, I go to a T, it's a 19. I go to my chart, go to an E, it's a 4. I go to my chart, to M, and it's a 12. Did not encrypt in that step. I only changed the letter to its corresponding number. But now that it is a number, I can encrypt using my key by adding 8. So I am going to add 8 to 18. I'm going to add 8 to 19. Going to add 8 to 4. And I'm going to add 8 to 20. I'm sorry, to 12, and I get 20. Well, that doesn't look much like a message. It looks like a bunch of numbers. So once I get those numbers back, I want to go and do alphanumeric substitution again, so that I can get a message that looks like a message. That's pretty easy with the 12. That will go directly to an M. That's pretty easy with the 20. It'll go to a U. But it's not so easy with the 26 and the 27. And that's because those letters are not, or those numbers are not on the table, on the chart. So when I added 5 to 9 on the clock and got 2, what I did was I got the remainder between the modulus, which was 12, and 14, which was the sum. So what I have to do here and here is get the remainder when I divide by 26. So I'll do 26 into 26 and 26 into 27. When I do 26 into 26, I get one remainder 0. So the 26 becomes a 0. When I do 26 into 27, I get one remainder 1. So the 27 becomes a 1. And I get A, B, M, U as my encrypted message. First step. Make sense? All right, so when we decrypt a message, we have to undo everything that's been done to encrypt it. So how do I undo addition? Somebody can write that in the chat. How do I undo addition? Subtraction. We're going to undo addition by doing subtraction. So take out your sheet that looks like this. It's got an alphanumeric cipher at the top. Alphanumeric substitution, sorry, at the top. And I'm going to give you the key. It's been encrypted with an additive cipher. It's been encrypted with a +12. And let's take a look at what you need to do. What are the steps for decrypting? So we're going to do number 11 together. TADEQ. So I see a T that has been encrypted with a +12. So to decrypt, I need to do a -12. I can't take 12 away from any of these letters because I can't, T -12 doesn't mean anything to me. So what I have to do first is change every single letter to a number. So I go over to the T, it's a 19. I go over to the A, it's a 0. Go over to the D, it's a 3. I go over to the 4. I'm sorry, the E is a 4. And I go over to the Q, and that's a 16. Haven't done anything in this step, This is the alphanumeric substitution. But now that they're all numbers, I can decrypt by subtracting 12. 19 minus 12 is 7. 0 minus 12 is minus 12. 3 minus 12 is minus 9. 4 minus 12 is minus 8. And 16 minus 12 is 4. So I ran into something I haven't seen before, and those are negative numbers in modular arithmetic. So we have to figure out what to do with those. Now, let me ask you while we think about this, what is 1 minus 3? Somebody can put that in the chat. Yes, minus 2. Now I'm going to ask you another question. If you start studying at 1 o'clock and you have been studying for 3 hours, what time did you start studying? 10. Again, if I write that in math, I actually asked you the same question in a different way. I got 2 different answers. They're 100% correct. Both of them are 100% correct. The difference is the second way I asked you related to the clock. Maybe you pictured a clock. Here's our same clock. And you started at 1 and counted backwards this time to get to the 10. But mathematically what you did was you actually probably thought it was minus 2, but you added 12, which is the modulus, to get that 10. So same thing here. I went too far backwards. I have to add the modulus. I have to mod 26. All of these numbers. The 7's already okay, and the 4 is already okay. Each of these other numbers, I have to add 26 to. And when I do, I get back into my range of values over here, so that I can reassign letters to all of these individual numbers because they're all on the chart. And when I do that, yep, I get it. So give everybody a second so these actually take a little bit longer. I do want to get to the puzzle at least slightly. So let's just take, I have till 7:30 today, so we can take our 7 more minutes, but let's take 2, see if we can get one of these, and then I'll give you the answers, but you know how to do the rest of it. Soda, yes. So this one over here is soda, so that's great. All right, well, let me just tell you, you can check the rest of these on your own. Number 13 is pasta. Number 14 is water. And the long one, title, is Einstein. And each of these then goes onto this sheet over here as part of the clue. The owner who keeps the horse lives next door to the one who eats donuts. The owner who eats hot dogs drinks soda. The German eats pasta. And the owner who eats burgers lives next to the one who drinks water. And this one, this long one at the bottom labeled title, actually goes up at the top. This is a variation of Einstein's riddle. It's a logic puzzle. And if you read the instructions on it, it says there are 5 painted houses on a block. So here they are up here. Here's that block. Each with an owner of a specific nationality. That's what's on the side. A pet, a favorite food, and a favorite drink. Arrange the neighborhoods and identify the owners of the fish. And I am going to share the screen right now. If you can see that. So there's a bigger version of that puzzle. And so there is no fish mentioned in this story. It's actually the last box left. So you have to arrange the entire block here in order to figure out who owns the fish. And I starred number 4 here. I want to show you a little bit. We have how many minutes left? 3 minutes left. So I want to show you a little bit about how you would set this up. So the easiest clue to start with is the one I starred. So the house colors are arranged in the order of the rainbow from left to right. So that's Roy G. Biv. So what that means is I know that the first house is red. The second house is orange. The third house is yellow. The fourth house is green. And the fifth house, there is no indigo. The last one is blue. So, so that's how you would set that up. And that would take care of clue number 4 right here. Then you have to go through the rest of these clues. They're not necessarily in order, but to figure out how logically they all work together. So for example, you know that the first house is red. Well, you look through the rest of these clues over here for something that either has to do with the first house or a red house. And I see number 9, that the Norwegian lives in the first house. So what I can do is assign that house to the Norwegian. And when I do that, to help me figure out what's going on later, I know that nobody else can live in this first house except the Norwegian, and the Norwegian can't live anywhere else. So it limits my choices for the remaining places. And you just keep going through that type of logic until you fill in the puzzle and solve the clues. So I can get this set for you when sent to you, or I can email it to you with the solutions when we're done. But because actually our time is just about up. And I wanted to see if we had any further questions before you leave from the chat. Anybody? So do you want me to, let me see if I have you're going to use it in your class. That's really great news. That's exciting. So I do like cryptography to lead somewhere. So hopefully that your kids will like it. Anybody have any questions or comments? I hope everybody's seeing how useful math is. All right, then with that, I will let you go. I'll see you tomorrow night. Tomorrow night, we'll be doing engineering design and on flight stability. So bring all your scissors, tapes, and supplies. Bye, everybody. Bye. Bye, Halida. TJ?